Hello and welcome to another one of D's ADD videos. Today we're going to be talking about the concept of Lewis structures. Lewis structures are a convenient and accepted method for keeping track of your valence electrons in a covalently bonded compound. You're going to be able to come up with the basic arrangement of the atoms, the number of bonds, also lone pairs, and it'll be a basis for coming up with the three-dimensional structure that you will be studying when you study Vesper in about a week or two, depending on your class's speed. So for now, what we need to do is look at elements. Elements on the periodic table. Elements on the periodic table each have their own valence number of electrons, and primarily we're going to be dealing with the group 1As, 2As, and 3 through 8. And you get the valence number of electrons from looking at the group they're in. So 1, 2, 3, 4, 5, 6, 7, 8. And basically what we're going to have happen here is we're going to write down the element. We're going to do carbon as the first one. Carbon's in group 4. So what we're going to do is do these two. So carbon being group 4 has 4 valence electrons. And what we do is we start on one side and you put an electron on each side until it's paired up. So again, put one on one side, and then once they're all on each side, then you can start pairing up. So chlorine, that's in group 7, if you were to go to your periodic table, chlorine's right here, group 7. So it's got seven valence electrons. If you were to put one on each side, then start pairing up, this is what you'd end up with. Not too bad. I probably won't do any example videos on that. What's more interesting is the compounds. So if they're cations, if there's a plus charge after your compound, make sure that you subtract from the total valence number of electrons, and if they're anions, you add whatever the charge is, because we've got extra electrons. Now we're going to draw a skeleton structure, and the skeleton structure is going to have the least electronegative element in the center, most of the time. Sometimes symmetry will cause issues, or sometimes restrictions like not having enough orbitals to make those bonds. Okay, hydrogen has only the S subshell. It only has one unpaired electron. It can only form one bond, so it will never be the center atom. I don't know. Just edit that part. Just symmetry is going to cause issues sometimes, and the more numerous element needs to be on the peripheral parts of the compound. Draw your bonding electrons once you've drawn the skeleton structure, and these are going to be lines, and each line is 2 electrons. For each bonding electron, we need to add them up and then subtract them from the number that we got in step 1. That's going to be the total number of valence electrons. The answer that we have left is going to give us our lone pair electrons. So then what you'll do is draw in your lone pair electrons and calculate your formal charges to make sure that you have the correct structure. All right, so if your formal charges don't add up to the net charge of the compound, then you probably did something wrong, or that's not the proper Lewis structure, or it's not a valid Lewis structure. How do you get formal charge? Just in case you forgot, there's a series of videos on that as well, but it's going to be the valence number of electrons minus the number of bonds plus each individual lone pair electron. Not the pairs, but each individual electron. Refresh your memory if you need to on formal charge. But just because you satisfy the rules that I just stated doesn't mean that it's the best and most stable Lewis structure. Okay? How do we determine what's the best and most stable? Well, we have to look for the structure that satisfies all the steps above and has the most bonds with the fewest formal charges. Again, that's the most bonds and the fewest formal charges. A few other things to watch out for is octet rule. What is the octet rule? Well, octet rule is going to be the rule that states that an element's going to want to have a full octet. It's going to want to have a structure similar to the noble gas in which all of its valence shells are filled. You can have an expanded octet for anything on the third row or lower. So that means we can have more than 8 total electrons around that atom. The reason why is because you now have access to the d orbital, the d subshell. We're going to do examples of these exceptions in probably the intermediate videos. Check that out if that doesn't make sense. But octet, you just want to have 8 electrons around carbon, for instance. So when I'm looking at carbon, typically you'll see carbon bonded to 4 other elements. Carbon bonded to 4 other things. That's a full octet. If you were to do a formal charge on carbon, that would be 4 minus 4 bonds plus 0 lone pair electrons, which equals 0. It's happy in its octet. But sulfur, you'll see sometimes will have the 4, but have some extra electrons or iodine or something further down the periodic table that has access to the d orbitals. All that's going to come up in the example video, so make sure you check them out. As always, practice, practice, practice is the key. This is very foundational for VSEPR theory and determining the 3D structures of these compounds and the bond angles and all that. So if you understand this well, you'll be well on your way to doing great on VSEPR theory. All right? Thanks for watching. As always, practice, 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 and have a great day.